Hello, seniors. It's been a while, and I'm glad to see you all again. Another journey is yet to overcome. Let's step ahead in learning another exciting area of science that concerned with the study of inanimate natural objects, including physics, chemistry, astronomy, and related subjects. Students, it's time to learn physical science. Our lesson today is how to write balanced chemical equations. At the end of this module, you are expected to explain the roles of subscripts and coefficients in chemical equations, balance a chemical equation when given the unbalanced equation, and explain the role of the law of conservation of mass in a chemical reaction. Even though chemical compounds are broken up and new compounds are formed during a chemical reaction, atoms and the reactants do not disappear, nor do new atoms appear to form the products. In chemical reactions, atoms are never created or destroyed. The same atoms that were present in the reactants are present in the products. They are merely reorganized into different arrangements. In a complete chemical equation, the two sides of the equation must be present on the reactant and the product sides of the equation. Before digging in the lesson, let's have these key terms. Chemical reaction, the process in which one or more substances are changed into one or more new substances. Reactants, the starting materials in a reaction. Products, materials present at the end of a reaction. Balanced chemical equation, a chemical equation in which the number of each type of atom is equal on the two sides of the equation. Subscripts are part of the chemical formulas of the reactants and products that indicate the number of atoms of the preceding element. Coefficient, a small whole number that appears in front of a formula in a balanced chemical equation. Before we go through the procedure, let's dissect a chemical equation and get a bit more familiar with its various components. Chemical equations provide a formula for a chemical reaction between molecules that may include a single element or multiple elements. These equations are neatly packed and presented arrangements of chemical symbols and numbers to describe a chemical reaction. A chemical equation can be grouped into two parts, the reactant and the product. The reactant is the one on the left side of the arrow with the chemical symbol of each participating reactant, while the products yielded by the reaction of the reactants are written on the right side of the arrow. Furthermore, the physical state of each element is also noted after their chemical symbols or formulas. S for solid, L liquid, G gas, and AQ is dissolved in aqueous or water solution. It is important to balance chemical equations in order to follow the law of conservation of mass. In simplified terms, the law states that there must be an equal number of atoms of each element in the reactants as in the products. There are two types of numbers that appear in chemical equations. There are subscripts, which are part of the chemical formulas of the reactants and products, and there are coefficients that are placed in front of the formulas to indicate how many molecules of that substance is used or produced. You cannot change subscripts in a chemical formula to balance a chemical equation. You can change only the coefficients. Changing subscripts changes the ratios of atoms in the molecule and the resulting chemical properties. The subscripts are part of the formulas, and once the formulas for the reactants and products are determined, the subscripts may not be changed. The coefficients indicate the number of each substance or molecule involved in the reaction and may be changed in order to balance the equation. There are two ways to balance chemical equations. First is the inspection or trial and error method. The second way is through algebraic method. The simplest and most generally useful method for balancing chemical equations is inspection, better known as trial and error. The following is an efficient approach to balancing a chemical equation using this method. Step 1. Identify the most complex substance. Step 2. Beginning with that substance, choose an element or elements that appear in only one reactant and one product. If possible, adjust the coefficients to obtain the same number of atoms of this element on both sides. Step 3. Balance polyatomic ions if present on both sides of the chemical equation as a unit. Step 4. Balance the remaining atoms, usually ending with the least complex substance and using fractional coefficients if necessary. If a fractional coefficient has been used, multiply both sides of the equation by the denominator to obtain whole numbers for the coefficients. Step 5. Count the numbers of atoms of each kind on both sides of the equation to be sure that the chemical equation is balanced. Let's apply these steps. Balance the chemical equation for the combustion of heptane. Step 1 is to identify the most complex substance. So the most complex substance is the one with the largest number of different atoms, which is C7H16. We will assume initially that the final balanced chemical equation contains one molecule or formula unit of this substance. The second step is to adjust the coefficients. Because one molecule of heptane contains 7 carbon atoms, what coefficient should we put in CO2 in the right side to balance the number of C or carbon? 7. Correct. We need 7 carbon dioxide molecules on the right side. So 7 carbon atoms on both reactant and product sides. Now, because one molecule of heptane contains 16 hydrogen atoms, we need 8 H2O molecules on the right side. Good job. So let's put 8 before H2O. So 16 hydrogen atoms on both reactant and product sides. Step 3 is to balance polyatomic ions as a unit. There are no polyatomic ions to be considered in this reaction. Step 4 is to balance the remaining atoms. The carbon and hydrogen atoms are now balanced, but we have 22 oxygen atoms on the right side and only 2 oxygen atoms on the left. 22 is the total of oxygen atoms from CO2 and H2O. So from CO2, 2 times 7 equals 14 oxygen atoms. For H2O, 1 times 8 equals 8. You look at the subscript of the oxygen. Okay, so 1 times 8 equals 8. Or you have to multiply the subscript and the coefficient. So the total of 14 and 8 is 22 oxygen atoms. Now, we can balance the oxygen atoms by adjusting the coefficient in front of the least complex substance O2 on the reactant side. So what number should we multiply by 2 to obtain 22? 11. Correct. 22 oxygen atoms on both reactant and product sides. Step 5 is to check your work. The equation is now balanced and there are no fractional coefficients. Let's check. There are 7 carbon atoms, 16 hydrogen atoms, and 22 oxygen atoms on each side. Always check to be sure that the chemical equation is balanced. The second example is the combustion of isooctane or C8H18. The assumption that the final balanced chemical equation contains only one molecule or formula unit of the most complex substance is not always valid, but it is a good place to start. The combustion of any hydrocarbon with oxygen produces carbon dioxide and water. So the most complex substance is the one with the largest number of different atoms, which is C8H18. We will assume initially that the final balanced chemical equation contains one molecule or formula unit of this substance. The second step is to adjust the coefficients. So the first element that appears only once in the reactants is carbon. 8 carbon atoms in isooctane means that there must be how many carbon dioxide molecules in the products? Yes, 8 CO2 molecules. Now we have 8 carbon atoms on both reactant and product sides. Next, 18 hydrogen atoms in isooctane means that there must be 9 H2O molecules in the products. 18 hydrogen atoms on both reactant and product sides. Step 3 is to balance polyatomic ions as a unit. Obviously, there are no polyatomic ions to be considered in this reaction. For step 4, we have to balance the remaining atoms. So the carbon and hydrogen atoms are now balanced, but we have 25 oxygen atoms on the right and only 2 oxygen atoms on the left. So why 25 oxygen atoms on the right side? So we have to compute the total number of oxygen atoms. From CO2, we have 2 times 8 equals 16 oxygen atoms. For H2O, we have 1 times 9 equals 9. And get the total, 16 plus 9 equals 25 oxygen atoms. But only 2 oxygen atoms on the left. So we can balance the least complex substance O2, but because there are 2 oxygen atoms per O2 molecule, we must use a fractional coefficient, 25 over 2, to balance the oxygen atoms. 25 oxygen atoms on both reactant and product sides. Now, the equation is now balanced, but we usually write equations with whole number coefficients. So how are we going to eliminate the fractional coefficient? We can eliminate the fractional coefficient by multiplying all coefficients on both sides of the chemical equation by its denominator, which is 2. So let's see. 1 times 2 equals 2. 25 over 2 times 2 equals 25. 8 times 2 equals 16. And 9 times 2 equals 18. And let's put these numbers into our chemical equation. You can have this. Lastly is to check your work. So the balanced chemical equation has 16 carbon atoms, 36 hydrogen atoms, and 50 oxygen atoms on each side. Balancing equations requires some practice on your part as well as some common sense. If you find yourself using very large coefficients, or if you have spent several minutes without success, go back and make sure that you have written the formulas of the reactants and products correctly. Let's have our third example. Aqueous solutions of lead nitrate and sodium chloride are mixed. The products of the reaction are aqueous solution of sodium nitrate and the solid precipitate of lead chloride. Write a balanced chemical equation for this reaction. So first step, again, is to identify the most complex substance. And the most complex substance in this equation is lead chloride. Next, there are twice as many chloride ions in the reactants as there are in the products. Place a 2 in front of NaCl or sodium chloride in order to balance the chloride ions. Okay, so 1 lead atom on both reactant and product sides, 2 sodium ion atoms on reactant side and 1 sodium atom on product side, 2 chlorine atoms on both reactant and product sides. Step 3 is to balance polyatomic ions as a unit. Again, as a unit. The nitrate ions or NO3 are still unbalanced. So we have to place a 2 in front of the NaNO3 to balance it. So let's check. 1 lead atom on both reactant and product sides, 2 sodium atoms on both reactant and product sides, 2 chlorine atoms on both reactant and product sides, and 2 nitrate ions on both reactant and product sides. Balance the remaining atoms. There is no need to balance the remaining atoms because they are already balanced. Check your work. Okay, so let's check again. 1 lead atom on both reactant and product sides, 2 sodium atoms on both reactant and product sides, 2 chlorine atoms on both reactant and product sides, 2 nitrate atoms on both reactant and product sides. So yes, it is balanced. This time, let's proceed to the second method in balancing chemical equation. Whilst the combination of algebra and balancing chemical equations might sound horrifying, it's not as bad as it sounds. The algebra part is pretty straightforward and precise. If you learn it, it can be a very fast way to balance difficult equations that are hard to balance by inspection. There are 2 algebraic methods, the normal algebraic method and a simplified version, which is the best way to crack the toughest equations. So let's look at the algebraic method first. The normal algebraic method. So the strategy for balancing chemical equations algebraically is as follows. Number 1 is write a different letter coefficient in front of each compound in the equation. Step 2. Write algebraic expressions or rules for each element that equate its atoms on the left and right sides. Step 3. Substitute and simplify to obtain a rule that equates only 2 letter coefficients that you can solve. Step 4. Substitute the values into the other rules to obtain the balancing coefficients. Step 5. Substitute the values of these letter coefficients to the chemical equation. That makes absolutely no sense, I'm sure, without an example. So here's an equation to balance using this strategy. So first thing to do is to write letter coefficient. Okay, so we give each compound a letter coefficient. As you can see, A, B, C, D, E, and F. Next, applying the conservation of mass, which tells us that the total number of atoms of each element must be the same on both sides. Write algebraic rules for each element. Let's start with potassium or K. The rule for K would be A equals D. We use equal sign to separate the coefficients for reactants and products. For manganese, we have A equals C. Oxygen is 4A equals F. 4 is the subscript of oxygen on this side, on the left side, from KMNO4. H is B equals to F. We put 2 because the hydrogen here at the product side has the subscript 2. And chlorine would be B equals to C plus D plus 2E. To explain the logic behind this using Cl as an example, we know that the number of chlorine atoms must be the same on both sides of the equation. On the reactant side, we would have a total of B chlorine atoms. On the product side, MnCl2 contains 2 chlorine atoms, so if its coefficient is C, it must contain 2 C chlorine atoms, whilst KCl contains the chlorine atoms, and so on, adding up the total number of chlorine atoms on the right side of the equation. Next is to substitute and simplify into 2 coefficients. So there are too many unknowns here, but we can substitute the rules for K and Mn, or for potassium and manganese, into the rule for chlorine to get rid of C and D. So we can have this: B equals 2A plus A plus 2E, or B equals 3A plus 2E. So we can also get rid of B using the rule for H. 2F equals 3A plus 2E. And finally, get rid of F using the rule for O. 2 times 4A equals 3A plus 2E. And 8A equals 3A plus 2E. 5A equals 2E, hence A equals 2 and E equals 5. Step 4 is to substitute the values into the other rules. Having now found two coefficients, substituting into the rules for chlorine and oxygen, and using the fact that A equals C equals D equals 2 solves for B and F. So B equals 2C plus D plus 2E, B equals 3A plus 2E. By substitution, B equals 3 times 2 plus 2 times 5, B equals 16. To get the value of F, for A equals F, for F equals 8. Step 5 is to substitute the values into equation. So remember our values. A equals C equals D equals 2, meaning A equals 2, C equals 2, and D is equal also to 2. E equals 5, F equals 8, and B equals 16. Then we have to substitute these values into our chemical equation. Okay? And after substituting the values into the chemical equation, check your work and count the atoms of each element. Let's count. 2 potassium atoms on both reactant and product sides, 2 Mn atoms on both reactant and product sides, 8 oxygen atoms on both reactant and product sides, 16 hydrogen atoms on both reactant and product sides, and lastly, 16 chlorine atoms on both reactant and product sides. And yes, it is now balanced. Now, if in the previous example you were thinking, hang on, if A equals C equals D, why introduce C and D at all? Why not simplify the whole thing? You would have been right, and this is where the simplified algebraic method comes in. So this method does exactly that. So it uses logic to reduce the number of unknowns you need to solve. It's the best method I know for balancing extremely difficult equations, and is a very fast method for balancing hard redox equations too. So once you get the hang of it. So the downside of it, if there is one, is that this method does need a little bit of intuition. By that, I mean some equations need you to apply certain balancing by inspection principles in order to simplify the algebraic methods you end up needing to solve. So what are the steps in simplified algebraic method? Identify the elements appearing only once on the left and right sides of the equation. So if the element is already balanced, write the same letter coefficients in front of its compounds. And if the element is not balanced, write the letter coefficient in front of the compound containing the greater number of its atoms. Then balance the element on the other side of the equation using the same letter coefficient, applying the conservation of mass. Second step is to place letter coefficients in front of the remaining compounds. Third is to minimize the number of letters needed by applying the conservation of mass and logic, so that coefficients representing an element on one side are expressed in terms of existing coefficients representing the element on the other side. Step 4. Write an algebraic rule for the remaining elements that equates them on each side of the equation. Substitute and simplify to obtain solutions for each letter coefficient. And lastly, use the conservation of charge principle wherever possible, as this can significantly reduce the number of unknowns. We'll use the same equation as the previous example to show how this works. The first step is to identify the element or elements appearing only once in each side. So obviously, these elements are potassium, manganese, and oxygen that appear once in each side. This time, we'll start by noticing that oxygen appears only once on each side. Applying the rules mentioned, we'll use the same letter coefficient in front of KMnO4 and H2O, putting A in front of KMnO4 and 4A in front of H2O, since logically, the number in front of H2O must be 4 times the number in front of KMnO4 to balance oxygen. Potassium and manganese also appear only once on each side, as does hydrogen, so the coefficient in front of KCl and MnCl2 must also be A. Step 3 is to minimize the number of letters needed by applying the conservation of mass and logic. So for hydrogen, the coefficient in front of HCl would have to be twice the coefficient in front of H2O, which is 8A. Okay, so that just leaves chlorine, which will give the coefficient B. Alright. So it's now possible to write an algebraic rule for chlorine. So 8A equals 2A plus A plus 2B, and 5A equals 2B, giving A equals 2 and B equals 5. The last step is to substitute the values of the coefficients. Okay, so we have 2KMnO4 plus 16HCl will yield 2MnCl2 plus 2KCl plus 5Cl2 plus 8H2O. So let's check by counting the number of atoms on both sides. So 2 potassium atoms in left and right side of the equation, 2 manganese atoms for right and left side, 8 oxygen, 16 hydrogen, and 16 chlorine atoms in both sides. So yes, it is balanced. That's the end of our lesson today. It's been my pleasure teaching you one of the amazing topics of physical science, and I really hope you learned something from this video lesson. Thank you, and may God bless us all. Let's meet again in our next video.